Now let's have a quick look at the fairly nasty formulas of the standard normal distribution and any other normal distribution. You can see now perhaps why we aren't integrating them. They're really no fun to deal with at all. But we need to have a look at these formulas just so that we can get some understanding about how they came about. Now both of them are based around this basic curve, y equals e to the power of minus x squared. Now you need to be able to graph this on Desmos. So my advice is to pause the video now, flick over to Desmos on another tab, and type in e to the power of minus x squared and have a look at what that graph looks like, and then come back and keep going with the video. Okay, you've had a look at that? Good. All right, now it's a basic bell-shaped curve, isn't it? But the problem is it wouldn't be a probability density function necessarily because it's positive in the whole domain, but it doesn't necessarily have an area under the curve of 1. And to be a probability density function, it really needs to fit that criteria. So what we've got here is the idea that the standard normal distribution has taken all of that into account. It's basically been transformed with dilations this way and this way so that the area under the curve is 1. Now, if we compare that to any other normal distribution and have a look at how on earth this formula has come from this one, you'll notice that this one is a function of z because it's our standard one with the z scores. This one is a function of x. So in fact, we should actually have x's over here. That was not right. They should be x's. Okay, now I've got two normal distributions here. I haven't actually drawn them very perfectly. I've just sketched them in. They're a little bit dodgy. But the idea is, for a normal distribution that's not a standard one, its mean will just be whatever it happens to be, depending on whether you're measuring the lengths of centipedes' legs or looking at anything it is that you're measuring. The mean could be positive or it could be negative, and that's up to what the data showed. Also, your standard deviation will be whatever it is. So this whole idea here is that this curve can be transformed. It can be slid across to where it needs to go to get to the mean. And we've done that by transforming the z, replacing it with x minus mu. But before that, it's actually also dilated and stretched to accommodate its standard deviation. Because on this curve, the standard deviation is 1, and that makes it really nice and straightforward. On these curves, the standard deviation will just be whatever it's going to be. So you'll notice on this one, the high point here is the mean, but this first point of inflection over here that's on either side, that would be the mean plus 1 standard deviation, or the mean minus 1 standard deviation, whatever that might be. And so that stretching affects the formula. Now, as soon as you stretch it sideways like that, you're now going to have an area under the curve that might not be equal to 1. So to accommodate for that, other dilations need to take place. You'll notice that the difference between these two is that we've got the standard deviation here, and that's a stretching in both directions then that accounts for that probability needing to be 1. Now, you don't need to know either of these formulas, but it is good to be able to recognize them so that if you see them on a page, you can go, oh, that's that nasty formula for the standard normal distribution. I've seen that before. So writing it down is not a bad idea, but put a great big note around it that says, don't need to memorize this. One thing you do need to be able to do, though, is you need to be able to graph this on Desmos. So now that you've got that tab open on Desmos, I want you to go in there and make up some data. Let's just pretend we've got a standard deviation of 5 and perhaps a mean of 60. Perhaps this results in a maths test, something like that. And you'll need to then put in this into Desmos as an equation and graph it. Because in our syllabus it says we need to be able to graph this using technology. So you'll need to just make a fraction, put in 5 multiplied by the square root of 2 pi, that's easy enough, e to the power of. Now here you'll need to just keep that as an x, that's your variable. Over here this is y. Minus mu will be 60. And here we've got 2 multiplied by 5 squared. So you can figure out what that is and actually just put that in as a figure. Could have 50 down the bottom there. So let's have a go at graphing that now.